Greetings, students. This is the third set of notes in the Freshwater Resources unit. The title is Groundwater. And like the other notes, you should be writing down everything with orange text. Pause the video if you need more time. So here is a diagram of some groundwater, including the infiltration part. Water needs to seep into the ground in order to create groundwater. And if groundwater has the ability to move with gravity, it always moves downhill. Some groundwater gets stuck in an aquifer if it's in contact with impermeable rock. Okay, so here's where we start writing. Anytime that you see water above ground, it's called surface water, like a lake or a river, the water that you see. But below ground, there is also always groundwater. Groundwater is often used for drinking water. Many major cities get their drinking water from groundwater. Most major cities in Virginia rely on rivers or wells for drinking water. Richmond gets ours from the James River. So wells would be accessing groundwater. But we're not talking about necessarily bucket wells. It's more usually of a high-tech pump sort of situation like you see here. Sediment is any part of the ground that is not solid rock. Smaller particles like sand, silt, gravel, and clay are sediments. Water can pass through some sediments, but not through others. And that's where we come to permeability versus porosity. Permeability is a measure of how well rock or sediment transmits water. Water will not pass through impermeable materials. So permeable versus impermeable. At the top here, we've got impermeable rock represented by the gray stripes. And then on the bottom, we have permeable sediment where there's spaces between the sediment. There's different pathways and they're all connected. When surfaces are impermeable, water does not seep into the ground and you have runoff, like pavement. A substantial amount of water is stored in permeable layers of soil and rock underground. That's your groundwater. Porosity. So porosity is different than permeability. This is the amount of empty spaces between sediment grains. Greater porosity does not always mean greater permeability. If the pore spaces in a rock are not connected, it can have a lot of porosity without being permeable. For example, this pumice here is an igneous rock, an extrusive igneous rock with air bubbles, but the air bubbles aren't connected. Therefore, this rock is not permeable, but it has a high porosity. Lots of holes, but they're not connected. With sediments, it kind of depends on the sorting. Well-sorted sediment, where all particles are the same size, has more pore space than sediment that is not well-sorted. Not poorly sorted sediment. It's particles of varying sizes, and you can see on the right side, the tinier particles fill in the spaces between the larger particles, so water isn't going to have as an easy time passing through as when they're all the same size, like on the left, where you have well-sorted sediment. So, is this sediment well sorted or poorly sorted? If you're paying attention, this one is poorly sorted because they're all different sizes. Would water flow through? Not particularly well. It might flow through a little bit, but no, not particularly well. Poorly sorted sediments are less permeable than well-sorted sediments, so water will not easily pass through. It's important to know that water always flows downhill. Most groundwater is moving towards the nearest lake or river. This is a diagram of groundwater that you'll have to get familiar with. The water table, if you're digging down from the surface, is where the water starts. Above the water table is the zone of aeration. There might be a little bit of water or air up there. Well, there's definitely air. There might be a little bit of water mixed in with the zone of aeration. But below the water table, it's saturated. The ground is completely full of water. And then in the middle there, you've got a well. Where the well is pumping, it's drawing down the water table, creating something called the cone of depression. So the water table is the area below which the ground is saturated or full with water. Beneath the water table is the zone of saturation. Above the water table is the zone of aeration. Here's another diagram of some groundwater features. When groundwater is between layers of impermeable rock, represented here by the dashed lines, it can be stuck underground in the same location for quite some time. So the permeable surface area that feeds the groundwater is called the recharge zone. If you have drought in the recharge zone, the water table will lower, it'll drop. So where the water table is located isn't always consistent. It depends on the amount of rain that you're having. Here's another version of the same diagram. Another thing that can cause the water table to lower is pumping from wells. Anytime people access groundwater for drinking, they are pumping it from the ground in some form of well. In order for a well to be successful, it must be dug deep enough to reach below the water table. So there's 3 wells in this diagram, and all of them reach the water table. The 2 on the left are reaching a confined aquifer, so between impermeable layers of rock, and the one on the right is just kind of in the regular water table. So if the water table were to drop a lot on the well on the right, that well might not be as successful as the ones on the left. Groundwater features. The area of the water table immediately around the well will drop due to pumping. This area is where the water table is lower. It is called the cone of depression. If you add more wells to the same area, the water drops even more. I already kind of talked about this. You'll have to fill this in on your own at some point, so you need to memorize this stuff. So here is 2 wells in the same diagram, and they're both drawing down the water table, so it's lowering. And you've seen this one already. Just be aware that the silty layer is impermeable, so it's creating a confined aquifer below it. And where the infiltration is occurring, that's the recharge zone for the confined aquifer. Saltwater intrusion. Near coastlines, saltwater can seep into freshwater aquifers. This is a natural process, but it can be enhanced through well pumping of the fresh water near the coast. So as you see in the diagram on the right, there's a well. The well is in the fresh water, but as it pumps more and more fresh water, it may draw the salt water towards it. The result is the contamination of drinking water sources. This is something that must be considered in the eastern part of Virginia near the Atlantic Ocean. Anytime you're close to the ocean, there is going to be salt water. Here's another diagram that shows 2 wells pumping, creating 2 different cones of depression. And then you have the salt water kind of creeping towards those wells. So well number 1 would be more in danger of saltwater intrusion than well number 2. Karst topography. Karst is a type of landscape where the rock below ground has been eroded by water. Certain sedimentary rocks are soft rocks, like limestone and dolomite. These soft rocks are easily eroded by slightly acidic groundwater. All rainwater naturally contains a small amount of weak carbonic acid. The result is a landscape riddled with caves, caverns, and sinkholes. Here is an image where you can see some limestone that's been eroded by water on a cliff face, and you can see all those caves. Karst topography is common in the Valley and Ridge Province of Virginia. This area is underlain by mostly limestone because it was once under the ocean hundreds of millions of years ago. This area of Virginia is known for some famous caverns like Luray, and there are also caves and sinkholes there. Here's Luray Caverns. So all of this used to be solid limestone, but as groundwater wore away at it, it created this large cavern. Oh yeah, A few years ago, there were some folks that were exploring in a cave in, I believe it was Thailand. It was like a soccer team, and they got stuck in there because there was a flood. So caves and caverns can be dangerous places if they're actively being flooded. The Chesapeake Bay crater. Over 35 million years ago, a large meteor struck Virginia. Under the Chesapeake Bay, there is still a crater from the impact, and it's very large. The meteor that struck the area was likely to be 10 kilometers in diameter. It fractured bedrock and aquifers in the area, leading to saltwater intrusion. And because of that impact, there are still pockets of ancient seawater trapped underneath the crater that can be studied by scientists. Pretty interesting stuff. So here's a map of the area impacted by the crater. And effects of the impact include land subsidence, that's sinking, broken aquifers, river diversions, unstable ground, and buried supersaline water. Back in the day, when the meteor hit, the ocean was a little saltier. So here's what your notes might look like if you type them up. You can also pause the page here and catch up on anything you missed. Of course, it's always okay to handwrite it as well, but this is going to go in your notebook. Have a nice day.